This is what we started doing in the last class, operational amplifier. We started looking at the characteristics of ideal operational amplifiers. Okay, and then I talked about the three main characteristics that are important when we are calculating the gain. The first thing is the assumption that the open loop gain is infinity. It's a very, very, very high gain. The second assumption is that the current going into the terminals of the op-amp is zero. Okay, and then the third assumption, fourth assumption, so on and so forth. But we use two of those, especially number 1 and number 3 when it comes to calculations. Okay, then we defined differential mode signals and common mode signals. In a very simple terms, the average of two inputs is called the common mode signal. The difference between them is called the differential mode signal. That's all there is to it. Then we looked at the idea of inverting amplifier, okay, where the input is applied on the negative terminal, the output is tied to ground. The resulting gain is that V output over V input is negative R2 over R1. Okay, so this is a negative gain, and hence the name inverting amplifier. And we saw how that is possible. Then we went into the idea of non-inverting amplifier, where the input is applied on the positive terminal, okay, and the resulting gain is the R2 over R1 plus 1. Notice that there is no negative sign here. The gain is positive. So meaning if the input is um, like so, the output is an enlarged version, an amplified version that is in phase with the input. Okay. Then we saw the idea of non-inverting amplifier as a feedback amplifier, okay, where I showed that 1 plus R2 over R1 is 1 over beta. Okay, so this idea, the approximation of 1 over the approximation of um, the gain to be 1 over beta, where 1 over beta is all of that guy, 1 plus R2 over R1. Okay, so this is what we looked at in the last class. Then we went on to talk about unity gain buffer, where the input is applied to the positive terminal and the output is tied back. Okay, so what is the beta factor here? When the output is fed back into the input, V output is that guy, the V feedback is this guy. Okay, what is beta?
1.
Beta is 1, right? Beta is defined as V output over VF. Okay, so this is supposed to be 1 VF over V output. So that is what all of the output is fed back into the input. Okay, negative terminal, the gain for this guy is 1. Okay, the gain for this guy is 1, hence the name unity gain buffer. Okay, and then we went on to talk about inverting summing amplifier, which is nothing but an extension of the inverting amplifier. As opposed to having one branch, okay, that corresponds to RF over R1 times V1. Okay, there are three branches shown using purple, using green, and using blue. And by the idea of superposition, you simply add them. The current, not necessarily superposition. The idea is that the current, the overall current that is coming in to these branches, to this node right here, is the sum of all the currents. Okay, by the idea that the sum of all the currents is the total current going into that branch. That is actually what goes out through the RF resistance. Then we can see it to set up the equation there. So summing non-inverting amplifier. Then we went on to talk about summing amplifier with positive and negative inputs. As you can see, there are two stages of op-amps. Okay, two inverting amplifiers. When you cascade them back to back, their negative gains multiply each other to give you a positive gain. So V1 and V2 shown at the extreme left, they have to go through two negative gain stages. So their overall gain is going to be positive. Okay, V3 and V4 on the other hand, highlighted using the reddish highlight here, they have to go through only one negative gain stage. So they have an overall gain of negative. So if you think about it, this amplifier, this a cascade of two op amps provides positive gain to V1 and V2 and negative gain to V3 and V4. So it's a summing amplifier with both positive and negative inputs. Okay, this is what we saw in the last class. Then we went on to talk about um, non-inverting summing amplifier. Non-inverting summing amplifier. Okay, here is where we use the idea of superposition. Okay, here is where we use the idea of superposition, and I illustrated the idea of superposition using this guy. Okay, when I'm evaluating the value of V2, I ground V1. That's exactly what I have done. There is V1 has been grounded. When I am evaluating the effect of V2, that's the idea of superposition, right? So I can calculate the fraction of V2 that shows up here. It's not V2 fully, but simply a voltage divider that is coming up because of V2, and that's this guy. A fraction of V2 shows up at that node, plus a fraction of V1 shows up through the voltage division of the superposition. And the sum of those two is the effective voltage, which is amplified by the 1 plus RF over R1. Okay, that's the non-inverting amplifier. Remember, this is the non-inverting amplifier gain. Okay, and then this is the effective. Uh, this is the effective um, voltage on the positive input. That times the gain gives you the output voltage. So in effect, what we have is V1 is amplified 6 times, V2 is amplified 4 times, then there is the positive time, there's the positive term. So here is a summing non-inverting amplifier. Okay, all of this we discussed in the last class. Okay, that's the idea. Then we are going to talk about difference amplifiers. Here is where we begin talking about difference amplifiers in today's class. But before that, let's quickly see what's going on and where we are. Okay, this week the idea is to be able to finish chapter. The idea is to be able to finish chapter 2 this week, and then tomorrow, which is the 4th, there's going to be a midterm. Okay, 4th, there is going to be a midterm. There's a slight change in plan. The idea was to proctor. The idea was to proctor the exam earlier, but I decided not to do that because some of you sent me an email saying that not everybody has access to a camera, and it's not possible. It's not fair for me to um, ask some of you to um, have your camera and let the others not have a camera. So you're going to take the exam tomorrow on your own, and it'll be between the class time 10 to 11:30. Okay, the exam itself should take 1 hour 15 minutes. So I have allowed for an extra 15 minutes of time in case you want to take a second attempt. It is possible for you to take a total of 3 attempts. Um, and so I added an extra 15 minutes of grace time for you to be able to take the exam a second time or a third time if you want to. Okay, the topics are going to be chapters 1 and 2, and it is not proctored. Okay, questions, please. Questions about the midterm. There is some practice exams on Moodle for you to follow. Okay, and like I mentioned yesterday, most of your learning has to come from the videos that are already posted on Moodle by Professor Headley. I'm only adding a little bit of information on top of what he already mentioned. So I may or may not be able to cover all the material in class, but you're welcome to watch the videos. Okay. So without further ado, let's continue talking about difference amplifiers. Questions? Let's see something in the chat. Are the number of problems the same as the practice exam? Yes, mostly within a plus or minus 10% difference. Okay, if we retake the midterm, will the problems be the same or will they be randomized like the quizzes? They'll be different. If you retake the midterm a second time, then you'll see a different question each time. Okay.
And like the distribution of marks with points will be also like that practice midterm.
Yes, mostly around that. Yes, very similar to the practice midterm. And then the maximum of your scores is counted towards the midterm. So you can use that to your advantage. Okay, so let's see other questions. All right, so let's quickly look at difference amplifiers. So the idea is I'm applying 1 voltage on the negative terminal and 1 voltage on the positive terminal. So far, I have done only one of those. I tied the positive terminal to ground and applied an input to the negative terminal, or I did the opposite. I tied the negative terminal to ground and applied a voltage on the input positive terminal. Now I'm doing both. Okay, so what I will see is that this amplifier is supposed to amplify the difference between these two. So in order to understand that operation, I'm going to define V input differential mode as the difference V input 2 minus V input 1. Okay, I'm going to define that. That's a definition. And I'm going to define the input common mode as the average between these two, VI2 plus VI1 over 2. Okay, and then I'm going to look at the output. Okay, the output over the differential mode input, that is going to be defined. I define that as a differential mode gain into the differential mode signals. Okay, and then I define a common mode signal to be the output voltage over the input common mode signals. Okay, so this is definitions, and what I really want is I want operational amplifiers to amplify the difference. So I want a really big differential mode gain and not amplify the common mode. Okay, I want a really small common mode gain. Okay, so if I define some performance metric, a differential mode gain over a common mode gain as some performance metric, I want it really to be infinity in the sense that I want a really, really big gain to differential mode signals. I want the OpAmp to amplify the difference between the inputs, and I want the OpAmp to attenuate or suppress these common signals. Okay, so if I define a figure of merit, that is the ratio of differential mode gain to common mode gain, I want that to be infinity. Okay, so V output again is defined as differential mode gain times differential mode input plus common mode gain times the common mode input. Okay, and you can simply plug those in. Oops. You can simply plug the value of IDM and ICM common mode, and then see how they turn out. Okay, so let's see differential amplifiers. Let's quickly analyze this using superposition. Okay, so let's simply look at the value of output V output 1, that is the result of simply V input 1. Okay, then we look at the value of the output 2 as a result of the V input 2, and then we add them. The overall V output is the sum of V output 1, that is the result of input 1 in the absence of V input 2, and then sum of V output 2. So sum of these two terms. Okay, and as it turns out, we don't have to reanalyze them. We already know the value for all of these. We already know the value for all of these. And as it turns out, when you're doing superposition, if you think about it, I'm tying this to 0 when I'm analyzing the value, when I'm analyzing the response of the op-amp to this V input. So this is 0, and then this is, there's no current flowing in to the op-amp that makes this guy 0. So this is a 0. So this is a circuit that I have analyzed already. So this is equivalent to, when I'm doing this superposition, this is equivalent to an op-amp. The positive terminal is tied to ground, okay, and the negative terminal input is applied. So that much I know. I know the gain of that guy. I know the output of that guy. That's what I have here, okay, because of superposition. Now let's do the other thing. Let's tie this guy to ground and look at the input that is coming out of here, okay, V input 2. Then what's the value of the, what's the potential there? Well, the potential there is going to be the voltage division R4 over R3 plus R4 times V input 2, which is amplified, which shows up here as well, which is amplified by 1 plus R2 over R1. That is the non-inverting amplifier. Okay, so the VO2 experiences a non-inverting amplification configuration, and this experiences an inverting amplification configuration. Okay, and the sum of these two is what gives me the overall V output. Okay, so V output is sum of VO1 and sum of VO2. That's the idea of superposition. And if I make the simplifying assumption that R3 is chosen to be R1, so this resistance is chosen to be that guy, and R4 is matched to R2, then I can see that the overall output, so pay close attention, the overall output is R2 over R1 times this guy, which is the differential mode. Okay, so this is the idea of difference amplifier. As you can see, for this particular set of values, where R4 equals to R2 and R3 equals to R1, the overall output is the difference of V2 minus V1 that is amplified by this factor R2 over R1. Okay, so that's the idea, that's the core, that's at the heart of a difference amplifier. Okay, therefore we can see that R2 over R1 times V input differential mode, that is by definition Vi2 minus Vi1, right? So what is the differential mode gain here? The differential mode gain is V output over Vi differential mode. So I take this to the other side of the equation. I'm left with R2 over R1 as the differential mode gain by definition. And the common mode gain it's easy to see that it is 0. Okay, so that's the idea of difference amplifier, which amplifies the difference between these two by a factor of R2 by R1. Okay, and this is built up using superposition.
I have a question. Like,
Yes.
what is the difference between this amplifier, like the difference amplifier, and differential amplifier? Is it the same thing?
At the core, that's exactly what is happening. Differential amplifier is looking at the difference between the input terminals and amplifying that. They're by definition the same. Okay.
Okay.
Here it's an op-amp that is being used as a differential amplifier.
Okay.
Make
But
sense?
differential amplifier is different from this, like kind of.
No, they're the same. The idea is there is a differential. If you look at what is sitting inside this op-amp, there are two stages. Okay, there is a differential. There are two stages inside. I'm talking about what is sitting inside this op-amp. So let me add a page here. So what is sitting inside this op-amp is typically two stages of transistor amplifiers. There is a differential stage, okay, and there is a common source stage. Okay, so differential stage, what it does is one of the inputs, V input negative is going into one transistor, V input positive is going into the other gate of the other transistor. So there's again a common current source over here. So the idea is there is some load sitting over there. So the idea is this is the differential stage, followed by a common source stage. And we are going to take a look at this to some extent in 108 and later on more detailed understanding in 109. But the idea is straightforward. The idea is that the difference between these two signals is amplified. And in this case, there is really no big difference. They're fundamentally the same. An op-amp that is used as a difference amplifier is by definition a differential amplifier. Make sense?
Yes.
Okay. All right. So this is a difference amplifier. So here is the definition that I talked about. Differential mode gain over common mode gain. Okay. And 20 log Baseline of that is defined as common mode rejection ratio in dB. And you want this to be extremely large. You want the common mode rejection ratio of a difference amplifier or a differential amplifier to be extremely large. Ideally, you want it to be infinity. Intuitively speaking, you want the op-amp to have a really big gain for differential mode signals. And for common mode signals, you want it to have a gain of 0. Okay, you don't want any amplification to signals that are common to both the terminals. Okay, so typically for practical circuit, that is ideal. I want the common mode rejection ratio. That is a measure of how well differential mode signals are amplified in relation to how well the common mode signals are attenuated. Okay, so for practical circuits, typically they tend to be anywhere between 1,000 to a million or 60 dB to 120 dB common mode rejection ratio. Okay, so common mode rejection ratio is typically limited by how well the devices match. See, earlier I defined certain relationships, right? So I I started out by saying that R4 should be equal to R2, and these definitions for V out were based on the understanding that R3 equals to R1. Okay, but then As with any circuit components, all of these resistances have some tolerances and they may or may not exactly match. As a matter of fact, it's more likely than not that they don't match. There is some tolerance, and that sets a limit, an upper limit on the common mode rejection ratio. So the common mode rejection ratio is typically limited by the match between devices. Okay, and like I mentioned earlier, there are some transistors sitting inside your OpAmp. So this is an inside view of OpAmp. And there typically will be some mismatches between the resistances there, between the two transistors that are highlighted there. Okay, these mismatches, okay, um, provide some kind of limit. They create some kind of limit to common mode rejection ratio. You typically want the common mode rejection ratio to be as close to infinity as possible, but because of device mismatches, you see that there's a limit. Okay, so that's the idea of differential mode circuits. Okay, difference mode amplifiers. Okay, now we can analyze this circuit a little bit more. See what I'm doing here. I'm applying a signal, V input differential signal between the negative terminal and the positive terminal. Okay, the differential input resistance is found by summing the voltages. So the assumption is that there is a virtual short here. Okay, so what I can do is I can create a loop, KVL, around that loop. Okay, so let me create a KVL equation around that loop. Okay, when I do a KVL around that loop, I can look at the voltage drop, okay, across this loop, which is the first resistance I1 R1, okay, that is I1 R1, plus there is a voltage drop of 0 across these two terminals, plus there is a voltage drop of I1 R1 across these two resistances, and um, minus VID, all of that should sum to 0. So the voltage drop along a path, along a loop, closed path should be 0, giving me the idea that VI differential is I1 R1 times 2. And my effort through all of this is to find the differential mode resistance RIDM, which can be evaluated to be VI differential mode over I1. Oh, that is the same as 2 times R1. So this is defined. So the differential input resistance is defined, is calculated to be 2 times R1. And R1 needs to be small for a high differential mode gain. And then R1 needs to be large for a high RIDM. So the idea is that there is a conflict here. There's a trade-off that we have to pay attention to. Okay, if you want to get a really big gain, which is what we always desire, then I want to make the R1 small. Okay, R1 has to be small. But if I want to make the input resistance RIDM, I want that to be a large number, as you can see. It's directly proportional to R1. So that needs R1 to be large. So it seems there's a trade-off. Okay, if I want, if there, it seems there's a trade-off between A differential mode and R input differential mode, in the sense that one needs the resistance to be small and the other needs the resistance R1 to be large. Okay, um, it's hard to find the union, find a happy marriage in this occasion between the gain and input resistance. So in order to solve that problem, we employ a different technique called instrumentation amplifier. Okay, if I'm using a single amplifier, it is hard to gain because that's going to cost my that's going to lower my differential input resistance. Or if I just shoot for a higher input differential resistance, that's going to lower my gain, differential mode gain. So I have to get out of this realm of a single amplifier to have best of the both worlds. How do I get a good gain and also at the same time the input differential mode? That's the idea of instrumentation amplifiers. Okay, in this case, okay, in this case, I get pretty good, excellent gain. Okay, so take a look at this. I'm not going to go into the analysis. I'm going to kind of behave like a lawyer here. Okay, there's a difference between how lawyers and scientists think, right? Lawyers have to kind of um, although that's not actually what it should be, that although not appropriate, lawyers tend to um, come up with a come up with a um, conclusion, and then put a logic around that conclusion. Okay, sometimes they have a um, lot of reasons to want to build a case around what they believe to be true. Okay, that's not how it's supposed to be, but lawyers build a case around the conclusion that they want to build. Okay, that's scientists, on the other hand, they begin with their logic, their reasoning, and their case, and then they eventually let that truth and their conclusions lead them, and their reasoning lead them to conclusion. Okay, so I'm going to behave like a lawyer here and start with the end in mind. So if you look at the gain here, pay attention to the gain. The gain seems to be R4 over R3 times 1 plus R2 over R1. Okay, there seems to be, if you can pay attention, the gain, there seems to be a multiplication of the gain here. So pay attention to the difference amplifier that we saw earlier. What was the gain of the difference amplifier? The gain of the difference amplifier was R2 over R1, right? That is for a simple difference amplifier. Let's see the gain in case of an instrumentation amplifier. Okay, the gain of an instrumentation amplifier is R4 over R3 times something else. Okay, it seems there is a significant multiplication of the gain. So it seems the instrumentation amplifier is giving us an improvement over the regular difference amplifier in terms of the gain. Okay, pretty good. Let us see the input resistance. What is the input resistance looking into the terminals here? Well, what is the current going into the terminal? That is essentially zero, right? The amount of current going into these op-amps is essentially zero. So the input resistance, R input, is infinity, and the gain, a differential mode, is also increased. So that seems to be a sweet spot where I can get a pretty good gain and a pretty good input differential mode, which is certainly an improvement over this guy. In this case, I could only get one at the expense of the other. But here, using instrumentation amplifiers, it seems I'm able to get the best of both the worlds, a pretty big gain and a pretty big input resistance. So that is the conclusion. Now, with that conclusion in mind, let me do the job of putting a case around it, analyzing this like a lawyer. Okay, I'm going backwards with the end in mind. So let's see, let's analyze this circuit. We see that there is, this is connected to ground, okay? And then this guy is going to be because of virtual ground, this is going to be a voltage division, and we don't have to analyze this circuit. We know that this is a non-inverting amplifier. Remember, the input is applied on the positive terminal and the input is tied back here through a pair of resistances. Okay, so this guy, if you pay attention to this guy, that is exactly the same. Let's go back up. That's exactly same as a non-inverting amplifier. Take a look here, okay? The input is applied to the positive terminal and the negative feedback is coming in through R1 and R2 to ground. Okay, that's exactly what we have here. And so we don't have to redo the math. We know it by inspection. We are able to write the, so that's exactly the same. Okay, so the input is applied to the positive terminal here and the negative terminal, there's a feedback. So it's easy to see why I have 1 plus R2 over R1 times V input 1 over here, because that's a non-inverting amplifier. Okay, that's exactly the same here. The input 2 is applied to the positive terminal, and then around that there's a negative feedback, and therefore I have a 1 plus R2 over R1 times VI2. Okay, that's the first stage. Okay, that's the inputs here. Now what I have here is a difference amplifier. Okay, the first stage is a non-inverting amplifier. Okay, then the second stage is a difference amplifier. Okay, that's exactly the same as this guy. Okay, this first stage, the second stage is exactly the same as a difference amplifier. So the gain of the differential amplifier is, it's easy to see that this is R4 over R3 times V input differential mode. That's the difference between this term and this voltage here. Okay, so it's easy to see that the difference between these two is 1 plus R2 over R1 factored out V input 2 minus V input 1, that is multiplied by R4 over R3 of the differential mode gain, and this guy is VIDM. Okay, so VIDM shows up on the other side of the equation. Therefore, it's easy to see that there are two stages here. The gain of the first stage is multiplied by the gain, differential mode gain of the second stage. So first stage is a non-inverting amplifier. The second stage is a difference amplifier. Okay, the gain of the difference amplifier is that guy. The gain of the non-inverting amplifier is this guy. Two stages cascaded. I have the overall gain to be the product of these two. Okay, and as you can see, the common mode gain is the differential mode gain is 1 plus R2 over R1.
Professor, like, what is the significance of the ground at point X?
Yeah, that's, as it turns out, um, it's an unnecessary thing. Not only is it an unnecessary thing, it's going to give us some kind of common mode gain as well, which is not a good thing. I don't want common mode rejection ratio to be 1. Because of this ground, okay, the common mode amplification signal is also going to be the same as the differential mode gain, which is a disaster. Remember, I wanted the differential mode gain over common mode gain to be infinity. But here, the differential mode gain and common mode gain um, are coming out to be the same value, 1 plus R2 over R1. So if I get rid of this ground here, so this ground initially was there because I was simply adding two of those non-inverting stages um, to two of the inputs. But let's see the magic that I can get by getting rid of the ground over there. Okay, by getting rid of the ground over here, okay, I'm going to use this guy. Okay, by getting rid of the ground, okay, what I have is two resistances R1 and R2 in series. Okay, that I'm going to redraw. Okay, I'm going to redraw that as 2R over here. Okay, that's because two resistances in series. And as it turns out, this has a much lower common mode gain. Okay, much lower common mode gain compared to the first stage. Okay, in this new version, the first stage gain for V input differential mode is the same as before. So the differential mode gain is still going to be exactly the same, but there is no current flowing through this resistance. If you think about it, and both of these signals are exactly the same. So common mode, V input common mode, okay? When that V input common mode, this turns out to be V input common mode as well because of virtual short. When I apply a V input common mode here, that shows up here as well, V input common mode because of virtual short. So the two ends of the resistance have the same voltage. So there is absolutely no current flowing through this resistance. And because there is no current flowing through this resistance, there is no current flowing through that resistance either. So the idea is the overall voltage is going to be a zero here. So the point being, think about it. If I apply this V in 1 not equals to V in 2, okay, when they're not equal, then V input differential mode gain is going to be the same as before. R3 by R4 by R3, yeah, R4 by R3 times 1 plus R2 by R1, okay, 1 plus R2 by R1, okay. But what happens when I apply the same signal here? When I apply, let's say, the V and V over here, okay, because of virtual ground, the voltage that I show here shows up here as well. And because of virtual ground, the same voltage V shows up here. And as you can see, both of these um, terminals of the resistance are at the same potential. So there is no current, meaning that the voltage that shows up there is zero. So the gain to input common mode is essentially zero. When I apply the same input to the terminals, then I have restored the common mode rejection ratio to be a very high value, which is the ratio of IDM over zero, which comes out to be a really big number. Does that make sense?
Yes.
So by removing the resistance here, by removing the ground there, I have connected these two terminals in such a way that there is no current flowing through this resistance when a common mode signal is applied. Okay, that's the idea of instrumentation amplifier. So what is the salient feature of instrumentation amplifiers? Very large gain and also a very large input resistance. Okay, and these are used in instruments, electronic instruments often, and therefore the name instrumentation amplifier. Okay, so the only cost though is that we are using more silicon real estate. We are using 3 op-amps as opposed to having just one op-amp. Okay, so instrumentation amplifiers are a special case of differential amplifiers. Okay, they're called differential amplifiers because they have a pretty big, okay, they have a pretty big differential mode gain and a pretty small common mode gain. So in effect, they're amplifying the difference between V1 and V2, V input 1 and V input 2. Hence, it's a differential amplifier. but the only advantage is that it provides a pretty large gain along with a pretty large input resistance. All right, so that's the idea of instrumentation amplifier, differential amplifier. Questions, please. Questions so far?
I have a question,
Okay.
Professor.
Yes.
I was trying some of the problems, like the exercise for meter 1,
Okay.
and it turned out the common mode gain for this circuit to be 1.
For the above circuit, it is 1. Yes.
Okay, for the one that you have in the following, like without the ground.
Without the ground, that's going to be 0. The common mode gain will be 0.
Okay.
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 Other question, please. All right. So let's see. Now, let's expand the idea of an operational amplifier. This is an inverting amplifier configuration, right? So we have seen the idea of an inverting amplifier where there is a negative terminal. The positive terminal is tied to ground. Okay, there is a resistance R1 over here. And there is another resistance, feedback resistance, R2 over there. Okay, the output, V output, is taken at that node. Okay, V input was over there. The gain, V output over V input, was earlier negative R2 over R1. Okay, and there's no compulsion, there is no necessity that these impedances have to be resistances. These paths can be frequency dependent components as well. I can have a capacitance in place of that resistance. I can have a resistance, an inductor in place of that, so on and so forth. So the idea is that Z1 and Z2, they don't have to be just resistances. These elements can be frequency dependent elements like capacitance or inductors as well. Okay, but the only problem is when we have frequency dependent components at high frequencies, at really high frequencies, okay, the loop gain, the A of the OpAmp begins to fall, and that violates the assumption that A beta equals to is much greater than 1. That leads to a problem, okay? Because the open loop gain drops off, open loop gain of the op-amp drops off at the high frequencies. Remember? Let me go back to the feedback configuration. We'll go back to the feedback configuration to talk about this. The assumption what is the assumption? The assumption was that A is much, much large. Okay, when A is very, very large, then the simplification was that I can approximate 1 plus A beta to be simply A beta. I can ignore 1 owing to the fact that A beta is a pretty large number. Okay, but if A beta is a small number, then I cannot ignore that 1. Okay, so at high frequencies, this assumption that A is a large number will not be valid. Okay, that is where this assumption gives me a problem. Okay, so if I can go back to these impedances, dependent sources here. Okay, if I can go back to the sources here, I can very well use frequency dependent components firmly knowing, knowing very well, and keeping in mind, being very careful that at high frequencies, the assumption that A beta is much greater than 1 will be violated. And so I have to be careful around extremely high frequencies. Okay, so besides that, I can use frequency dependent components in place of the impedance Z1 and the feedback impedance Z2. And this can be used to build many interesting circuits like integrators, differentiators, and filters. Okay, so let's see, let's take a look at integrator. Okay, it's an inverting integrator. Okay, inverting integrator, because pay attention to the negative sign here. That's a negative sign. When you convert an integral from a voltage domain to the Laplace variable, an integral in a voltage domain becomes 1 over s. Okay, in an integral 1 over s times. That's the Laplace transformation. But let's quickly see what is going on here. I replaced this resistance. Earlier I had a resistance R2. Okay, the gain of this guy, V output over V input, was negative R2 over R1. Okay, that was the gain. Well, that's exactly what I have here as well, except that this is an impedance Z and the resistance is R1. This is an inverting integrator. Okay, so by replacing the resistor in the feedback loop with a capacitance, we get an inverting integrator. So the idea is this. So the voltage across the capacitance is integral over 1 over C, integral of the current. Okay, integral of the current plus any initial conditions, any voltage that existed on the capacitance to begin with at time t equals to 0. So most oftentimes what we do is we short these capacitance using a shorting switch between these two terminals at time t equals to 0. That way there is no residual initial condition there. We begin with an initial condition of 0 by making this guy 0. Okay, that way we have an integrator, a current that is integrated. The current that is flowing into the capacitance is integrated to be its voltage. Okay, so I1, we know I1 of t is Vi of t over R. Okay, because this is 0 here. The current that is flowing into this resistance I1 has to flow through this capacitance. The same idea, because the current flowing into the OpAmp is 0. Therefore, I1, we can see that it is Vi input over T of T over R. That's the current flowing through this resistance, which happens to be the current flowing into the capacitance here. And therefore, we integrate for a voltage across this capacitance, VC, okay, we have to integrate. Okay, we integrate 1 over C times the current. Now, V output, pay attention to the fact that V output is exactly the opposite of negative V output is negative V times C, because it is looking from the other side of the capacitance. So if this voltage is plus VC, then this voltage is going to be negative VC. Okay, so that's the idea. So we pick up a negative sign when we look at the output voltage here. Okay, so the output voltage is negative times V capacitance of T. So I can express V output to be negative integral. So all of this is I of T, I1, that divided by R, that divided by R. Okay, so that's the idea of integrator. Okay, so if I express this in the frequency domain, this integral converts to a 1 over S. The rest is all the same. There is 1 over RC. There is 1 over RC here, and a negative term coming in there, and a negative term coming in there. Okay, so this is called the transfer function, V output of S over V input of S. It's a single pole behavior. Remember, there is a negative 20 dB per decade roll off. Okay, the gain at DC, what is the gain at DC? So if I express this as j omega, the complex frequency variable j omega, DC means omega equals to 0. So when I plug in a 0 into this, I get a DC gain of infinity. Okay, I get a DC gain of infinity. Let's see how we can get a DC gain that is a bit more predictable, that's a bit more reasonable. Okay, so all we have done is
Professor, can you a little bit of explain like that 20 dB one, 20 dB decade, where did we cover it?
yeah, where did we talk about the 20 dB per decade, right? So let's see amplifier basics. When I go back to the body plots that I discussed for the OpAmp, right here. Okay, a pole. Okay, there's a pole here at that frequency. At the pole frequency, remember, the gain begins to roll off at 20 dB per decade. This is what we discussed for a low pass STC single time constant circuit, where the gain begins to roll off at negative 20 dB per decade. Remember when I discussed the body plots?
Yeah, how do we define like pole?
Yeah, it is this guy, a single resistance and a capacitance. Remember, there's a low pass. This product, 1 over RC. RC has units of time. Remember, 1 over RC has units of omega, right? Or radians per second. Now, the idea was that this guy, it turns out to be a pole frequency, RC. If you plot the frequency response, just like you did in the first lab, you will see that the gain at DC, if it was 100 dB, let's say, at the pole frequency, it will be 97 dB, 3 dB below. Okay, if you go to 10 times the pole frequency, you'll see that it's going to be 77 dB. Okay, you can verify this using your frequency analysis, and you'll see that for one decade change in frequency, for a 10x increase in frequency, the gain will come down by 20 dB. Okay, so that's the idea, and this is simply an expression of the frequency response of the amplifier. Okay, the frequency response of the amplifier. This is nothing but, if you think about it, this is nothing but you're plotting gain. So look on the x-axis. What is on the x-axis? Frequency, right? On the y-axis, what is on the y-axis?
Gain.
V output over V input, the magnitude in dB, gain, right? So let's look at the extremes. Let's look at one extreme where, let's see, the omega equals to 1 over RC. Okay, then this omega and this RC cancel out each other, and you take the magnitude of that, you are left with 1, and you take a dB of that, log 1 base 10, 20, you get a 0. Therefore, you see a gain of 0 dB at the pole frequency. Does that make sense? Look at the other extreme where this frequency is 0. Okay, what is the frequency? When the frequency is 0, you'll see that it'll asymptotically approach infinity. When the omega is 0, then all of this denominator becomes 0. Then the gain, the DC gain of this is infinity. Okay, so it's easy to see. I'll show you why. Let me quickly show you why. Add a page. Okay, let's see. I have an amplifier that looks like this. Okay, so there is a resistance here, and there is this guy is connected to ground. This is negative terminal. Now I have a capacitance C, and I'm trying to apply an input. The frequency of this is 0 hertz, or this is DC, right? Now, what do you think happens to this capacitance at DC?
Open circuit.
It's going to behave as an
Lock.
open,
Lock.
correct? So now, all of a sudden, instead of having a feedback configuration, I am left with an open circuit gain, an input that is applied to the negative terminal of the OpAmp here. And what was the assumption? The assumption was that the open loop gain is infinity. Therefore, the DC gain at DC is infinity. We want to have a more predictable, a more reasonable gain, and we make a small modification to that. Okay, so this is the idea, the transfer function of a single time constant, single pole behavior here. Okay, so let's see how we can modify this integrator just by adding a resistance in parallel to the capacitance here. Okay, now what I can see is, in addition to the 1 over SCRF here that I have seen earlier, so there is this 1 over SCRF, the same term here. By adding the resistance in parallel, I have an additional 1 plus term and an additional RF over R term. Okay, so it's easy to see. What do you think happens at DC now? If I am to evaluate what happens at DC, the capacitance behaves like an open circuit. Okay, now I have reduced at DC, I have reduced this op-amp to a negative feedback configuration. Okay, at DC, this this S becomes 0. So all of this denominator goes to 0. So I'm left with just one term here, because this S plus CRF, this goes to 0. Okay, so I'm left with all of this term goes to 0. So I'm left with 1. So you can see this is reminiscent of a negative RF by R, which is reminiscent of a negative inverting amplifier gain. So the idea is, at DC, an integrator reduces to an inverting amplifier, and at higher frequencies, I have a gain that corresponds to this. Okay, so that's the idea. By adding a resistance in the feedback in parallel with the capacitance, we can limit the low frequency gain. Earlier, the low frequency gain was infinity, but now the low frequency gain is just negative RF over R times 1 plus S over RC, 1 plus S times RC. Okay, as you can see, the V output over V input is always ZF over ZS. Okay, ZF, this is ZF. We know that negative feedback, negative inverting amplifier V output over V input is the resistance impedance in the feedback over this resistance R. Okay, so from that understanding, with a negative sign, from that understanding, That's exactly what I have here, ZF over R. But ZF is nothing but a parallel combination of this resistance RF and a capacitance whose impedance is 1 by S times C. Okay, so that's a ZF is a parallel combination of RF and SC. Okay, so integrators with infinite DC gain are usually avoided because small DC voltages, that's a bad thing, because earlier when I had an infinite DC gain, a small DC voltage is always saturated to positive or negative power supply. I don't want that. So what I do is I want to have a more predictable, a more reasonable DC gain. And I get that by incorporating a resistance in parallel to this capacitance. Does that make sense? So this is an integrator with a finite DC gain. Earlier I had an integrator. Earlier, except that its DC gain was infinity. Okay, if I plug in a value of omega equals to 0 there, the gain is going to go to infinity. I don't want it. I don't want small DC voltages to saturate my output. So I want to have a more predictable and more reasonable DC gain. I can get that by simply adding a resistance in parallel to this capacitor. Okay. Let's see. Let's talk about differentiators now. Earlier I had a capacitance. Earlier I had a capacitance here in the feedback path and a resistance in the input side. Now I switched them around. I have a capacitance between the input and the negative terminal, and then I have a resistance in the feedback path. Okay, now this turns out to be a differentiator. Okay, an inverter, an inverting configuration, still a negative terminal. Okay, and then the reason is the current I equals to C dV by dt. Okay, we know that for a fact that I is C dV over dt for a capacitance. Okay, so the voltage that is applied here to one side of the capacitance produces a current that is proportional to the derivative of the current. Okay, now I can express V output. So that's the same current. So this current I is flowing through this resistance R. Therefore, R times this current I will give me the voltage that is dropped across this resistance. And then V output is going to be the negative of that resistance, of that voltage drop. Okay, so all I'm doing is expressing the current here in terms of the voltage. Okay, and then I can see that the current entering this branch equals to the current leaving in this branch through R, and therefore the voltage dropped across that is negative R times the current. Okay, so the voltage drop V output is negative R times I. All of this is I, right? The current flowing through I. From that, I can see that V output over Vs, the transfer function, has an RC time constant in the numerator. Okay, it's an RC negative S times RC, because a derivative in the voltage domain translates to a S in the Laplace variable domain. Okay, so if I express it in terms of omega, I see that the gain V output over V input is negative J omega times RC. Okay, so if we explore the value of this at the extremes, at omega equals to 0, the gain is going to be really, really small. The gain is going to be 0. So at omega equals to 0, or at DC, omega equals to 0, we know for a fact that all of this gain is going to be, the gain of this guy is going to be 0, because I plug in a 0 here. Okay, that leads everything back to 0. And at really high frequencies, at omega tends to really large values, I have a really large gain. Okay, so that's the gain. If I plot the gain as a function of omega, I can see that it's a high pass response. It's going to have a small gain for low frequencies and a big gain for higher frequencies. Okay, that's the idea of a differentiator. Using a capacitance, um, all I'm doing here is a really straightforward technique, expressing the current I in terms of the capacitance. Earlier, what I did was the exact same thing. When I had a resistance here and a feedback resistance there, I expressed the current I is V over R. Here, I'm doing the exact same thing, except as C dV by dt. Yeah.
So, like, is there any difference between this differentiator and the one we did earlier, like differentiating amplifier?
Oh, these are the differential amplifier is different.
Okay.
The differential amplifier is quite different from the differentiator. Okay, the
So
differentiator.
it this one do that mathematical differentiation.
Thank you. This does the mathematical derivative of the input voltage. So as you can
Okay.
see, um, it is called a differentiator because the output voltage is the derivative of the input voltage. Earlier, in the differential amplifier, the V output was the gain of V input 2 minus V input 1. Okay, so the difference between the two inputs is amplified in a difference amplifier, whereas in a differentiator, okay, the derivative of the input is amplified, and that's why it is called a differentiator. Does that make sense?
Yes.
Okay, so we are looking at the different uh, circuits that we can build out of op-amps. Okay, so we looked at differentiator, integrators with a finite DC gain, instrumentation amplifiers, quite a bit. Okay, so we are making good progress. Okay, so that's the idea of differentiators. And as it turns out, that the integrator with a finite DC gain that we looked at earlier is actually a low pass filter. Okay, actually an active low pass filter. Okay, if you think about it, the low pass filter had a transfer function. That's the transfer function of a low pass filter. Okay, and then that is amplified by some ratio of RF over R, and hence the name active low pass filter. So an integrator with RF in parallel with capacitance can also be viewed as an active low pass filter. Okay, this guy is the omega 3 dB frequency. Okay, the gain at really, really low frequencies and at DC, that's the DC gain. So if you think about plotting it, okay, this guy, plotting frequency in terms of the log AV base 10 of 20 in the x-axis, you'll see that this value is RF over R, 20 log base 10. Okay, so the DC value of the gain is going to, magnitude of gain is going to be RF over R, and you can take a dB of that. But the idea is the integrator with RF in parallel can also be thought of as a low pass filter. Okay, with a low pass filter, and because there is a single pole behavior, single time constant, the roll off is always going to be negative 20 dB per decade. Okay, it's going to be negative 20 dB per decade, and it turns out that the pole frequency for this guy, the frequency at which this begins to fall, is 1 over RC. Okay, that's the negative 3 dB frequency. In the last class, the day before yesterday, you were all doing the DC, the AC analysis, and found that exactly 5.310 kilohertz, the gain was 3 dB, negative 12 dB. It was 3 dB below the DC gain. Remember? That's exactly the idea here. So that frequency is going to be 1 over RC times 1 over RC. Okay. So that's the idea of active low pass filter. So let's quickly review all the circuits that we did so far. Okay. In today's class, we started looking at difference amplifiers. Difference amplifiers simply amplified the difference between the two input voltages. Okay, the difference between these two, VI2 minus VI1, is amplified. But then that came at a cost that I could only increase input differential mode gain, or I could only increase the input resistance, but not both at the same time. So in order to do that, what I did was to have an instrumentation amplifier, which let me increase the differential input resistance and also the differential mode gain to a large value. Okay, but then one kind of differential amplifier with a ground here gave me some common mode gain as well. I don't want that common mode gain, so I got rid of the ground over here, and then the common mode gain came down to 0. Okay, so that is the instrumentation amplifier, which can give me pretty good gain and also pretty good input resistance. Then we looked at amplifiers with impedances, frequency dependent components, integrators, where a capacitance is included in the feedback configuration. I found out that this is called an integrator because the output voltage is an integral of the input voltage times some amplification. Okay, so it's called an integrator. And then the transfer function of that expressed in frequency domain looks like so: 1 over j omega r times c. Okay, this implies that I have an infinite DC gain. I don't want an infinite DC gain. So what I will do is I include another resistance in parallel to the capacitance in the feedback. Then I have a finite DC gain. The DC gain is simply this guy, RF over R, a predictable, a much more manageable finite DC gain. Then we went on to talk about differentiators, which include a capacitance between the input terminal and the input voltage, and the feedback is a resistance. So this turns out that the output voltage is the derivative of the input times some gain, hence the name differentiator. And I saw that it has an RC in the numerator, and then At the extremes, the DC gain of this guy is 0. Okay, the DC gain of this guy is 0, and the AC gain at high frequencies is going to be very high. Then I mentioned that this particular circuit integrated with a finite DC gain integrator is also an active low pass filter with a pole frequency of 1 over RC, which is the negative 3 dB omega, and then the gain rolls off at negative 20 dB per decade. Does that make sense?
So
All
in
right.
this last circuit, if we substitute the capacitor with an inductor, so the circuit is going to work as an active high pass filter. Would that act as an integrator as well?
Well, it's not going to act as an integrator. It's going to have a different frequency dependence. Okay, L di by dt. Okay, the voltage across this guy is going to be L di by dt, and that is what sets the behavior of this circuit over here. Okay, when I have an inductor in place of a resistance, the governing equations becomes V is L di by dt. And based on that equation, I have a different behavior.
So
Okay,
can we call it
now
a differentiator?
I'll have to look into that and see if it behaves like LDI by dt. I'll have to take a closer look. Okay, so let's revisit the idea of ideal effects of op-amps. Earlier, I made some assumptions about operational amplifier, right? The first assumption that I made was that the open loop DC gain is infinity, okay? Infinite open loop DC gain, AV, is infinity, okay? And the second assumption that I made was that there is no current, II, going into an op-amp is 0, okay? And the third assumption that I made was that it has an infinite bandwidth, okay? The third assumption. And then all of these assumptions that I made about an ideal op-amp, well, they're not all true. It was only to understand how the op-amp is supposed to behave as opposed to the real behavior of an op-amp. Okay, in reality, what happens is a lot of the assumptions that I make about the op-amp are not, they're only true in the conceptual world. They're not true in the real world. Okay, and then a lot of those assumptions have an effect on the behavior of real world op-amp. Okay, so let's take a look at the first assumption that there is an infinite gain. Okay, so what I will show you is that what happens to the overall error, okay, as the DC gain approaches from infinity, a really large number, to a small number. Okay, the assumption, as you can say, I'll show you the big picture. If the gain is small, the error is large. If the gain is large, the error is small. Okay, as the open loop gain approaches infinity, so limit A tends to infinity, as the open loop gain approaches a large value, the error, there's a limit to the error becomes small. Okay, so what error am I talking about? The error in approximating A over 1 plus A beta to be 1 over beta. That's the approximation I'm making, right? So this guy, all of this, I'm approximating the heart, at the heart, I'm expressing 1 plus A beta to be A beta. So A by, I'm getting rid of that A beta. I'm getting rid of this 1. That's the approximation I'm making. That leads to an error. Okay, if I get rid of this one, that leads to an error. Okay, this error becomes a small number as this value of A increases. Okay, on the other hand, as the value of A becomes small, the value of error increases from a very small number to a very large number. So that's the idea. So there is some approximation that I'm doing. I'm approximating 1 plus A beta to the A beta. Therefore, I can simplify this A and A to leave a 1 by beta. The error in that approximation increases as the value of A decreases. Okay, so that's the problem. So the error is essentially zero when the AV is infinity, when the open loop gain is infinity. That was my first assumption, right? The open loop gain is infinity. But if the open loop gain is not infinity, then the error is going to increase. Okay, so that's the idea. As you can see, at really small gain, the error is going to be a big number. At a bigger gain of 1000, the error is going to be only plus or minus 1%. Okay, as the gain goes down, the error goes up. What is the effect? The effect is that the overall gain that was supposed to be V out over V in for an inverting amplifier, that was earlier negative R2 over R1 in the ideal case. Okay, and I'm not going to walk you through the algebra here. I'll just point to you the final result. Okay, the overall gain is not R2 over R1 anymore, but it is smaller than that. See, even in the case of a non-inverting amplifier, earlier non-inverting amplifier, the ideal case was just the numerator. But in the presence of a non-ideality of a finite DC loop gain, so the AV is not infinity anymore, then the overall voltage gain is smaller than the ideal value. So compare this guy, compare it with 1 plus R2 over R1, which is the ideal case. Okay, the overall closed loop gain here is less than the ideal scenario. Similarly, in the case of an inverting amplifier, you would expect to see negative R2 over R1 in the ideal scenario. Okay, but the real world value is less than the ideal value. So you have a smaller gain. That's the idea. So this is the real world. On the right is a non-inverting amplifier. On the left is an inverting amplifier. So the effect of finite DC open loop gain is that the overall closed loop gain is smaller than the ideal scenario. Okay, there are a few other non-ideal effects. The input offset voltage. What happens if there is a mismatch between these two terminals? Okay, and what if the current that is going into the OpAmp, I initially assumed that to be zero. I input assumed to be zero. What happens if there is some current going into the OpAmp? So there are certain non-idealities that deviate the behavior from the ideal scenario. Okay, so I don't think I have time to go into that right here, but then there's a little bit of gap that I'm leaving, and I ask that you read through that. Okay, so questions so far, please.
Like offset voltage is like the voltage which the like the amplifier.
I can give you a hint about the offset voltage. So in the ideal scenario, okay, let's take a look at the ideal scenario. When the input voltage is 0 on that guy and 0 on this guy, what would be the output voltage?
0.
It should be 0, right? But sometimes what happens is, because of mismatches between the transistors that are sitting inside the op-amp,
Okay.
even when the inputs are fully 0, the output is going to be a non-zero value, okay? V output, okay? When the V input is 0, V output, ideally you expect it to be 0, but in real world it is not 0, okay? So if you divide the V output by the open loop gain of the circuit, you get what is known as input offset voltage.
Okay.
Does it make sense?
So it's kind of like error voltage.
Yes, yes. That error is coming because of the mismatch between the um, circuit components that are sitting inside the op-amp.
Okay.
Okay?
Okay.
All right. So here is the idea. So we'll take a look at this graph. Okay? When the value of the input differential mode is 0, you would expect the output differential mode to be a zero value. But as it turns out, when the input value of the input differential mode is 0, the output is not 0. There is still some output value that is non-zero. That's the idea of offset voltage, okay? And it leads to a lot of, it's easy to fix just by incorporating an additional voltage source on the in, okay? All right, so I want to stop here.